This is Mr. Anderson for Math 121, Kellogg Community College. We're going to be looking at the first section of our Chapter 3, which is going to be looking at solving systems of equations with two variables. Now, if I just give you an equation like 2x plus 3y is equal to 6, this will make it a line. But it won't give us one answer for x or y because a line has an infinite number of points. But if we were trying to solve when two lines intersect each other, we need two equations to do that. And there are times where lines intersect at a point, like crossing like an X. Sometimes where the two lines are parallel, where they never cross at all. Or there are times where one line is written the same, is the same as a second line, but they are written in a different form to maybe trick you a little bit into thinking they were two separate lines, but in fact they were the same line. We're going to be investigating all of these graphically in this section. Because when we have two variables in an equation, we can't actually solve for x or y specifically. We would need two equations to solve for x or y if and when they intersect. So in this chapter, we're going to be looking at situations where we have an x and we have a y, and we have another x and another y in another equation, and we're trying to ask the question, will these lines intersect? Will they be parallel? Or are these two of the same lines that happen to be written in a different way? So our first skill is to check to see if the point is the solution of both equations. So here we have your first part of your homework where it gives you a point 4, 0, and it wants you to see if that happens to be the intersection of these two lines. To solve for this problem, you're going to plug the 4, 0 into the equation itself. So I'm going to put these together like so, and then solve by simplifying. 2 times 4 is 8, plus 7 times 0, which is 7, which happens to be equal to 8. So we at least know that 4, 0 works in the first equation. We just need to see if it works in the second equation. So I'll plug my 4 in for my x, and 0 in for my y, using parentheses for my substitution, and I then simplify there. Negative 9 times 0 is 0, 4 is equal to 4, and there we go. That shows me that this point gives the correct response in both equations. So yes, this is a solution. These two lines cross at the point 4, 0 or the x-intercept. So yes, this is a solution. Now let's look over here and see how this works out. We're going to plug in negative 5 in for my x and plug 1 in for my y and see if that equals 0. Well, let's go simplify that. Negative 5 plus 5 times 1, which is 5, is equal to 0. Therefore, negative 5 plus 5 equals 0. 0 is equal to 0. And therefore, we have the first equation seems to check out, but let's try the second one. Let's plug in our y, which is 1, is equal to 2 times negative 5 plus 9. So I've got 1 is equal to negative 10 plus 9. Simplifying that, negative 10 plus 9 is negative 1. So unfortunately this does not pass. The first one did and the second one didn't. So this is not a solution to where these two lines intersect. They will not intersect at these points because they're not true equations for both of those. Alright, and after you get done with that first part of your homework, the next part is going to be to see how things go when you graph. Now, we're going to graph by hand to see if there is a solution to these problems. And we're going to talk about consistency and dependency, which is two vocabulary words that you're going to see a lot in this section. So the first thing I'm going to do is I'm going to evaluate which may be the easiest way to graph these lines. I've got two methods to graph. I can either graph using the slope-intercept form, or I can graph using intercepts. Now, since my x and my y are pretty plain and my 3 is all by itself, I'm going to choose the intercept method. So to solve for my x-intercept, I'm going to plug 0 in for my y. So I'm going to make a little table here, and I'm going to graph 2 points. There we go. Let me draw that down there. I'm going to plug 0 in for my y to solve for my x. So this is going to find my x-intercept, so if I plug 0 in for y, I get x is equal to 3. So there's 3 right there. I am now going to solve for my y-intercept, so I'm going to plug 0 in for x. So I'm going to plug 0 in for x, and if I do that, that gets kind of covered up, and y is equal to 3. So there are my 2 points. I'm going to go to my graph over here. 3, 0 is 3 to the right, and 0, 3 is 3 from the bottom. And I'm going to take my line and just kind of draw it like this. Now this is where having a straight edge would be really important, because you're going to find out that things are really quite important to see where these line up. So let's go back to drawing, but I'll change colors here. I'll change to a green, and we'll check to see the other line here. Let's see, we got y minus x is equal to 1. Same thing about finding intercepts. I'm going to find my x-intercept, so I'm going to plug 0 in for my y. And if I plug 0 in for my y, I got negative x is equal to 1. Dividing both sides by negative 1, I've got my answer of x is now equal to negative 1. So there's my first point at negative 1, 0. Now to find my y-intercept, I'm going to plug 0 in for my x. If I plug 0 in for my x, I just get y equals 1, which puts me right here. Now this is where having a ruler really helps out. And you'll see that if I had a perfectly nice line there, then the intersection of these 2 points would be right here at this spot at 1, 2. So this is my intersection, 1, 2, and that's my solution. Your solution has to be written as an ordered pair, because we found the x and y where these lines intersect graphically. So from here, we also need to talk about the vocabulary word consistency and dependency. So let's talk about what that means. Consistency talks about whether there is a solution to the problem. So this is consistent. It's consistent, and the reason why is because there's one solution. Now, I would strongly recommend that you try to remember that consistency is used when there is a solution. It could be one solution, it can be many or infinitely many solutions, and we'll see that example at the end. Now, whether this is independent or dependent, this is considered independent because there were 2 lines. And these 2 lines were given by their separate colors, the blue and the green. So these are considered independent lines that are consistent with one solution. And we got 2 more examples to go. Okay, case number 2. Now, what's great about number 2 here is that case number 2 has the first equation is already in slope y-intercept form. So I'm not even going to do the intercept method. I'm just going to go to my graph and plot the points. So I'm going to have this be the blue line. So let me go start where it starts, which is at negative 2. And then from there it's going to go down 3 over 1, because slope is given by rise over run. So negative 3 over 1, so down 3 over 1. And if I wanted to add an extra point in there, I could go from here up 3 left 1 and still get these points. And I can do that one more time. Up 3 left 1. There we go. And now I make my line. Again, a straight edge is probably very beneficial right now because we're going to try to see when these things graph and work well. Okay, now just for kicks, instead of using the intercept method here, I'm going to use the slope y-intercept method. So instead of making a table, I'm going to solve by moving my 6x to the right, draw a line. So 2y is equal to negative 6x plus 10. And then we divide everything by 2. So now I have x, sorry, that shouldn't be an x, that should be a y. Y is equal to negative 3, because negative 6 divided by 2 is negative 3, x plus 5. So I'm going to go to my 5 there. I'm going to go down 3 over 1, which happened to be the same slope as this equation up here. Down 3, 1, 2, 3, and over 1. Down 1, 2, 3, and over 1. And again, having a ruler is probably very beneficial here, but I think you kind of see what the solution is here. The solution is that there is no solution. These are parallel lines. We learned in the previous chapter that parallel lines have the exact same slopes. So our solution is no solution. There is no solution to the problem. Now let's get back to the two vocabulary words. Is this, first of all, consistent or inconsistent? Well, this is inconsistent. And it's inconsistent because it has no solution. And I think I should try to have you memorize that consistency has to deal with whether there is or isn't a solution. And since this is inconsistent, it's inconsistent because of no solution. Now, is this independent or dependent? Well, this is again independent, like the last equation. And it's independent, well, because there were two lines. There were two parallel lines in the problem. Okay, last example. All right, moving on down to the bottom here. So, here we go. Okay, and for our last problem here, we're going to take a look at seeing where these two lines cross. Now, I'm going to take my first line. Let me make it blue here. Now, I'm going to use, let's see here, should I use the slope y-intercept method or the intercept method? I think I'm going to use the intercept method. I'm going to first of all solve for my y-intercept by plugging 0 in for my x, which gives me 3y is equal to 6. Because negative 2 times 0 is 0. Mentally dividing both sides by 3, I get an answer of y is equal to 2, so there's my point. Then we're going to move on to the next part, which I'm going to plug to find my x-intercept. I'm going to plug 0 in for y, so negative 2, x is equal to 6. Divide both sides by negative 2, x is equal to negative 3. So negative 3 comma 0. Draw a line, and there it is. Now I get to see what my next equation is going to be. I'm going to use, for this case, I'm going to tackle the slope-intercept form right here. And, you know, you can use the intercept method like I just did with the table. I just am going to take it a little different direction here. So let me go there. Okay, so I'm going to use the slope-intercept method, and I'm going to go minus 8x from both sides. All right, that looks good. So I got negative 12y is equal to negative 8x minus 24. Divide everything by negative 12. I'm going to have some simplification to do here. So this is going to be x is equal to, simplify that to, well, two negatives make a positive. So it's going to be a positive 8/12, and then I can simplify that by dividing each by 4, so it becomes 2/3 x plus 2. So I'm going to start at the dot, which is the 2. Maybe that's an intersection point. I'm going to go up 3 over 2, and then when I do that, if I go up 2 over 3, sorry, I misspoke there. If I go up 2 over 3, I missed my dot there. You're going to see that I'm going to have this line that's going to go, as I said, up 2 over 3. Oh no, these are the same lines. These are the same lines because they went on top of each other. So the solution is that you actually have all real solutions. But let me show you the way that we should write this answer here. Since these are basically the same lines that they're overlapping each other, you're going to use some set notation. X comma y. That is for all points x and y. This equation is true. And you can pick one of your two equations because it doesn't matter. You can pick any of these two equations because it's going to be true for all of them. And now finally we're going to talk about consistency and we're going to talk about dependency. Well, were they consistent? Oh yeah, they were definitely consistent. And they were consistent, well, oh, I forgot my S there. S-I-S-T-E-N-T. Sorry about the little spelling error there. They're consistent because they're all solutions. They're overlapping lines, so it's because they have all real solutions. And that means if you plug any number in for x and y in this relationship, it will show up on this line. Now, is this independent or dependent? Well, this is the last one, and it is dependent, and it's dependent because they're the same line. They are not two independent lines. So, in summary, consistency works if there is a solution, whether it's all real solutions like in overlapping lines, or in one solution with intersecting lines. Dependency has to deal with if they're separate lines, and in this third example, they were not separate. Well, thanks for watching.